In this question, we've been told that the number of accidents that a certain police force were asked to attend over a period of 86 days is summarized in the table below. So we've got intervals of accidents from 0 up to and above 11. We've been asked to use a chi-square test at a 1% level of significance to investigate whether the above data can be modeled by a Poisson distribution with a mean of 6 accidents per day. Okay, so this is a goodness of fit test. We've been told the distribution is Poisson, and we've been given a parameter. This means that in our hypothesis, we should refer to that parameter. So I'm going to go ahead and say that H0, x follows a Poisson of 6, is a good fit for the data, and H1, x following a Poisson of 6, is not a good fit for the data. This time around, the significance level is 1%. But the first thing we need to do, as always, is to try and find the expected values. The expected values are going to come from the Poisson calculation for these number of accidents. And then we're going to scale that by 86. So the probability that x is in between 0 and 2 when lambda is 6, I'm going to multiply that by 86, and I get an expected value here of 5.332. Similarly, the expected frequency of days where there were 3 or 4 accidents is going to be the probability of this Poisson distribution equaling 3 or 4 multiplied by 86, and that gets us 19.187. And we'll continue this all the way down and we'll generate all of these expected values. As we're generating these, we realize that they're starting to get smaller. When looking at these, we do need to check if any of them were smaller than 5. And I could see in the group 11 plus, yes, that expected frequency is smaller than 5. I'm going to need to do some combining, and those expected frequencies will be combined, plus the observed frequencies would be combined as well. So let's just summarize that with the observed and the expected that we're going to use in our calculation. The group 8 to 10 and 11 plus are being combined into a group that we'll call 8 plus. Here's the observed and the expected that we'll be working with. And now that I have all of my expecteds, I can go ahead and calculate our test statistic. So the degrees of freedom, that is going to be the number of rows we have at the moment, which is 6 minus 1. That gives me degrees of freedom of 5. From there, I can look up the critical value for 1% and 5 degrees of freedom, and we get 15.086. That's our critical value on a diagram that will be placed here, and any test statistic that is in the shaded region, any test statistic greater than 15.086 is going to lead us to reject H0. It will be a significant result. Let's go ahead and find our test statistic. Our test statistic, we're going to use the sum of the observed squared over the expected minus n. So we're just going to generate these fractions. For each of these fractions, it's the observed, the black number, squared over the red expected frequency. And we'll just continue that for all of these 6 pairs. And at the end, we'll subtract n, the number of days we were working with in the first place. We're going to subtract 86. And from that, we get an answer of 14.5. That is our test statistic. Is it significant? It's over here on the left-hand side. It's outside the critical region. It's outside the significance region. It's outside the rejection region. We do not have a significant result. Let's formalize that with the comparison. 14.5 is less than 15.086. It's less than the critical value, so it is not significant. And we'll follow that up with our conclusions, our standard 2-part conclusion. The first being a mathematical conclusion, we do not have enough evidence to reject H0, and the second being in context. There is not enough evidence that X following a Poisson distribution of 6 is a good fit.